there, this is the second set of notes in Unit 2. Notes B is all about light. So we're going to look at electron transitions, and how that can produce different sorts of waves. And some of these waves are light. Generally speaking, we say these notes are about light, but we will look at a little bit of the electromagnetic spectrum beyond that. As you can see here, we even have some sound waves like AM radio waves, FM radio waves, and even some nuclear rays like gamma rays or X-rays. So all sorts of different waves can actually be produced from transitions inside of an atom. The electromagnetic spectrum actually categorizes different types of electromagnetic radiation. So there's two main things that you're going to see patterns on here. One is called wavelength, and that's characterized by the Greek letter lambda. And then we have frequency, which is the Greek letter nu. Now the typed versions of these letters aren't coming out so great. Usually lambda would be a bit more curvy with a little kickstand, and nu is kind of half V, half U, just so you know. Although the wavelength more defines the actual color that we see or the type of radiation that there is, and the frequency is actually more defined by how much energy the particles have, or later we'll get into this, the photons have. There is actually a relationship between wavelength and frequency. And of course, where there's a relationship, there's a formula. So this is that formula. So we would say nu equals c over lambda, or the frequency is equal to the speed of light over the wavelength. So where the wavelength increases, the frequency decreases, and vice versa. C is a constant. So it is equal to approximately, and this is rounded to 3 significant figures, approximately 3.00 times 10 to the 8th meters per second. That is the equivalency of the speed of light in space. So that's why it says in a vacuum. I think this picture does a better job of explaining what wavelength and what frequency really are. Better definitions with the picture. So for wavelength, it would be the distance from one crest or top of a hill to another crest. Of course, that would be the same distance from what they call trough to trough, or if you do actually know what a complete sine wave is, it would be a complete sine wave as well. But you have to get the entire wave. So that is an entire wave length, the distance from one part of a wave to the next part of the wave. Frequency is a little bit harder to picture. Imagine I'm holding my hand at the edge here, and this wave is actually moving. Kind of like a heart rate monitor you've seen on the TV movies, beep, beep, beep. Like imagine the heart rate monitor moving from left to right. In order to count the frequency, I would hold my hand at the corner here, and I would count how many waves hit that point in a given second. So what do you think the relationship is between the wavelength and the frequency? Yeah, as the wavelength would get smaller, if I had waves that were closer together, more of those peaks would hit my hand in a given second. So if I had an decreased wavelength, I would have an increased frequency. On the flip side, if I had nice calm waves, I would have a larger wavelength, right? Crest to crest would be longer, a bigger wavelength, but then I would have less crest hitting my hand per second. So where one goes up, the other goes down. We call that inverse. Let's try a calculation. In this problem, it gives us the frequency of the violet light, and then it also gives us the frequency of the red light. But we're going to calculate both. We're going to separate them. So let's first focus on the violet light. Now I want to calculate the wavelength. So the wavelength would be the lambda, and I'm going to plug in my constant speed of light and the frequency that's given in the problem. So on top, the speed of light, the constant, is always 3.00 times 10 to the 8th meters per second. This constant is on your cover sheet for this unit, and you should have that cover sheet with you when you take the test. On the bottom, we're going to plug in the frequency, and that's what was given in the question. 7.31 times 10 to the 14th hertz. So math-wise, it's a lot for the calculator, but at least you should know what the division looks like, right? We take the top, divide it by the bottom. So in the calculator, I would plug in 3.00, or just 3, the scientific notation number, E, or not number, button, E, and then just the 8. Then I'd hit enter and hit divided by 7.31, E, 14. So you get that all in your calculator, you should get the number answer. But we have a huge issue with the units here. This is a hot mess. None of this cancels. Let's pull this off to the side here. I've got meters per second divided by a hertz. What's helpful is this. What the heck is a hertz? So hertz is the SI unit for frequency. It's how many waves per second. Anytime you have per second, anytime you have per anything, that thing goes in the bottom. So if it's per second, the second is in the bottom. So instead of saying hertz, I could use an inverse second, or a second on the bottom. Now what do you do if you have a fraction over a fraction? That's our reciprocal trick. So instead of 1 over s on the bottom, I'm going to have s over 1 on the top. And when I multiply that across, the s's cancel, and I'm left with meters. So my unit for the wavelength would just be meters, which is kind of good for length, right? Even though it's a wavelength, it's still a length. So meters is perfect. So now it's just up to you and the calculator to get the number of 3 times 10 to the 8th divided by 7.31 times 10 to the 14th. What's your final answer? And our final answer, 4.10 times 10 to the negative 7th meters. For sig figs, we have three significant figures with both factors. You go by least sig figs for division, so our final answer also has 3 sig figs. So yes, you need that 0. 4.10 times 10 to the negative 7th meters. Now let's do this for the red light, which has a frequency of 4.57 times 10 to the 14th hertz. So that frequency would be what we plug in for nu. We're going to calculate the wavelength just like we did on the last example with the violet light. The c is still the same. It's still the speed of light, a constant of 3 times 10 to the 8th. So let's start setting this up. What should we plug in on the top? On top will always be the speed of light, 3.00 times 10 to the 8th meters per second. On the bottom will be our frequency, which for the red light is 4.57 times 10 to the 14th hertz. First question, what will be the unit for my final answer? It would be meters. The meters per second has the second canceling out because the hertz was the same thing as an inverse second. So that second ends up canceling out when you do the reciprocal, and so you just have meters for that final answer. Now what do you get for your numerical answer? Let's figure out how to get this in the calculator. What is the wavelength for the red light? The wavelength would be 6.56 times 10 to the negative 7th meters. Let me go on a very short tangent on, just in case you're using other resources for looking up how to do wavelength. If I'm in visible light, not invisible, if I'm dealing with visible light, the exponent should be negative 7. They tend to express this in nanometers, so that means that we're multiplying by 10 to the 9th. So this actually becomes 656 nanometers. So that's a more common way of expressing visible light, is to switch it to nanometers so that you're not dealing with scientific notation. So I just wanted to make that connection. As long as it's a -7, you just make this like however many hundred. Now that we've finished everything we need to know about light as a wave, the wavelength, the frequency of how fast, how much energy the wave has, I want to break light down to a particle level. There is such thing as a particle of light. That's called a photon. In order to get light to break down into photons, you need something called a spectrum. So a continuous spectrum would be where white light is passed through something called a prism, and you get the entire spectrum, continuous spectrum, no interruptions. That continuous spectrum is known as a rainbow. So when we look at a red particle or a purple particle, we're referring to the individual photons. Now here's the super important part. Each photon has a specific amount of energy. The amount of energy is known as the quantum. So I think that's one of the more important vocabulary words in this section. The quantum is the amount of energy that a photon has. And that's going to determine the type of light or electromagnetic spectrum energy that we get. So earlier we talked about how the energy is directly related to the frequency. So here's the formula that relates those two things. The energy is related to something called Planck's constant times the frequency. So again, this typed out version of Planck's constant isn't perfect. It should be a little h, lowercase h, with a little hat on it, a little cross on the top. So that would be something called Planck's constant, which is just like the speed of light, always the same number. Constants don't change. So we're just going to plug in this number anytime we see Planck's constant. It's going to give us the frequency and we solve for the energy, or vice versa. And you can see here that the unit for frequency is still hertz. If you didn't know, the unit for energy is the joule. Now let's calculate the energy of those violet and red lights from before. So here I have the frequency that we determined earlier. Now I want to use that to find the energy. So for the violet light, I'm going to start with the energy is equal to, we have our formula here, Planck's constant. So Planck's constant was 6.63 times 10 to the negative 34th joules times seconds. By the way, that is joules times second, not joules per second. So that's my Planck's constant. I'm going to multiply that times the frequency, 7.31 times 10 to the 14th hertz. We're going to run into the same problem we had before. Hertz isn't going to do me much good with the joules and the seconds. So I'm just going to go ahead and use that 1 over s that we know it is. What that's going to allow me to do is cancel seconds on the top and seconds on the bottom, so that I know my seconds cancels out, leaving me with joules, which is perfect for energy. So now it's about the calculator once again. We need to figure out how to type in 6.63 E negative 34 times 7.31 E 14. What do you get for your final answer? We should get 4.85 times 10 to the negative 19th joules. Notice how everything has 3 sig figs. We're going by the least number of sig figs. So again, 4.85 times 10 to the negative 19th joules for a violet light. So now for our red light, we have the red frequency we had determined in the last calculation, 4.57 times 10 to the 14th hertz. Now I'm going to plug in E equals HV. What did the H stand for again? Oh, that was Planck's constant. So that's 6.63 times 10 to the negative 34th joules times seconds. And then we're going to multiply by that by the frequency, which we have here for the red light. We had found to be 4.57 times 10 to the 14th hertz. Let's see if you can finish this one on your own. So to get the units to cancel, you have to turn the hertz into the inverse seconds, and then the seconds will cancel, leaving you in joules. And then for the math, when you multiply, you should get 3.03 times 10 to the negative 19th joules. Now we've done two different types of calculations. In one calculation, we looked at the wavelength, and in the other calculation, we looked at the energy of a photon, or particle of light. There's not a lot of things in the world that can act as both a wave and a particle. We call this the dual nature of light, and it's a fairly special property of light, the ability to act as both a wave and a particle. There are a lot of scientists involved in this discovery that you should know and have in your notes for your AP test, but I'm not going to put these scientists on our honors chem test. I'm going to focus on the scientists from the atomic theory for honors chem. But I would go ahead and copy these down for your IB or AP tests. You'll recognize Planck, the first one, from Planck's constant, and Hertz, the second one, from the unit for frequency. So each having, like Planck having something to do with the photons. For Planck's constant, we calculated the energy of the photons, and then Hertz was the frequency, which was related to our wavelength. Then we had a few other people involved here. Of course, you recognize Einstein. We did talk about Bohr with the atomic theory, and then someone named de Broglie. Now that we've talked for a while about light itself, why in the world are we talking about light when we're supposed to be studying atoms? So let's tie this into what the light actually has to do with transitions inside of an atom. So it all comes down to movement of electrons. So first you have to have some terminology behind this. Whenever an electron is in the lowest possible energy level, which by the way it likes to be in because electrons are lazy, we call that the ground state. It's grounded, low energy. But then if it gets excited, if it has more energy, it can go to a further energy level. We call that the excited state. So we have the ground state that's closer to the nucleus and the excited state that's further out. The excited state has more energy than the ground state. Whenever you have a transition between these states, you're going to either absorb or produce some sort of wavelength. So that's going to give us kind of an idea of what transitions are able to happen inside of each atom. These are unique to an atom, kind of like a fingerprint. So you could actually kind of play matchup. If you pick up an emission from a star, you could then compare that to known elements and figure out what elements are present in that distant star. This is actually something that they do to study stars. So we can actually determine which elements are present based on an emission spectrum. The catch about an emission spectrum, about emitting light, is that it would have to occur when energy is emitted. Remember we said the excited state had more energy? So the emission would happen as the electron falls from the excited state back down to the ground state. This is super important to know. It's not going from ground to excited. That would require an input of energy. The emission occurs as we go from excited back down to the ground state. I mentioned electrons like to be in the ground state, so that will happen automatically. I mean, they have to be excited in the first place, but then they will automatically fall back down to the ground state, and that'll be when we get emissions. There is also such thing as an absorption spectrum. This would basically look like a continuous spectrum, kind of the opposite of what we just saw with the emission spectrum. And instead of having black with colored lines, you would see colored with black lines. So imagine a rainbow, but you would see black little lines in the same way that you saw colored little lines on the last slide. So that's representing where color would be absorbed, where the electrons are going from the ground state up to the excited state. So with absorption, we're moving from the ground state up to the excited state. It's absorbing energy, so we're seeing a lack of color, aka black lines. I think it's pretty important to kind of draw out what would happen in an electron transition. So here I have a picture of 3 different energy levels. N represents something called a principal energy level, so it's like the first energy level, now we have the second energy level, the third energy level. Electrons like to be on the lowest energy level, so the very first electron would fill in on that first energy level. Let's say I excite that electron. Maybe I set the atom on fire. We're going to do some flame tests in this unit. So if I excite it with fire, the electron might bounce out to a higher energy level. So the energy level where it was, the original lazy level, is the ground state. But whichever energy level it chooses to go to would be the excited state. And it'll only have certain ones to choose from based on which atom it is. So let's say this atom has a transition from the first energy level to the third energy level. So now that electron now is no longer in the ground state and is now in the excited state. So here's where my electron is at the moment. Well, it doesn't like to be there. Electrons are lazy. So they will automatically say, screw this, I'm going home, and head back down to the ground state. That's going to happen automatically no matter what. That's just the way electrons are. Now let's think about the energy during all of this. In order for the electron to go from the ground state to the excited state, it would have to go from low energy to high energy. So in order to go from low to high energy, there would need to be an input of energy, hence the absorption spectrum. But as it goes from the high energy to the low energy, it would need to lose energy. So that's going to have to go somewhere. That loss of energy can't just magically disappear into thin air, right? According to the law of conservation of energy, energy cannot be created or destroyed. So that energy has to go somewhere. It's going to be emitted in the form of a photon. And the symbol for a photon, by the way, is a little gamma symbol, a little curly Y guy. So that photon is going to come out. And the amount of energy that this photon has is going to be determined by the amount of energy that's between these two levels. That energy loss is going to go directly into the photon. And then that photon's energy is going to determine what kind of frequency it has, and in turn what wavelength it is. It's going to determine what type of particle it is. It's a huge transition. It's going to be something dangerous, like a gamma ray or an X-ray. If it's a very small transition, then it might be something more innocent, like maybe visible light or a sound wave. So the type of wavelength produced all has to do with the amount of energy. What was that vocabulary word for the amount of energy? The quantum. A quantum of energy, the amount of energy between the transitions, which in turn becomes the amount of energy the photon has. At the end of all this, I want to try to go through two examples that are involving a couple of different steps. So the first one, we have a wavelength given of 486 nanometers. I mentioned earlier that wavelength in visible light is often measured in nanometers. So yes, you can use system of equations throughout all of this just to head off that question. If your algebra is there, go for it. I'm going to do this just a step at a time and then move into the next step. So first thing I want to do is get rid of nanometers and go into meters, so that way it'll work with my other equations, like the speed of light being in meters per second. So this conversion is going to be done through dimensional analysis. So we got 486 nanometers. Put that over 1. And whatever's on top, I will put on the bottom. So nanometers to the bottom. And I'll convert to meters. So 1 meter is equal to 10 to the 9th nanometers. A conversion that you could look up on your conversion factors sheet or your things to know and love. 1 meter times 10 to the 9th nanometers. So that means for meters, we have 4.86 times 10 to the negative 7th meters. So that's what I'm going to use for my wavelength. Now I'm being asked for energy. So these are the two equations we're given. This one was one of those ones that we can come up with through systems of equations. So again, feel free to go ahead and use that. but I want to break it down step by step. So we've got this wavelength that we could plug in, and then that's going to allow us to find frequency. So let's start there. The frequency is equal to the speed of light, which is the 3.00 times 10 to the 8th meters per second. And then I'm going to divide that by our wavelength we have here of 4.86 times 10 to the negative 7th meters. So my meters will cancel, leaving me with a second, but notice that that second is in the denominator. Isn't that perfect for frequency? 1/second, also known as a hertz. So now we just need to get this in the calculator. 3 times 10 to the 8th divided by 4.86 times 10 to the negative 7th. What is the frequency of this particle? Or I should say wave. So for this part, we should get 6.17 times 10 to the 14th. A common mistake with these light calculations is to leave off the rest of the scientific notation. Just because you're rounding the main number, the 6.17, to the correct sig figs, doesn't mean you can forget the rest of the calculator. Look at the end. See that E14? That means times 10 to the 14th. Now starting from that frequency, we can use the formula energy is equal to Planck's constant times nu. So E equals 6.63 times 10 to the negative 34th joules times seconds. Make sure you have the constant with you for the test. And then you're going to multiply that by the frequency we just found of 6.17 times 10 to the 14th inverse second. So the seconds cancel, and what we're left with is joules, which is perfect for energy. So what do we get when we multiply these two numbers? We should get 4.09, and then look towards the end of the calculator, times 10 to the negative 19th. Make sure you convert that back to times 10, by the way. Don't leave that as the E. That's not how you rate things in real life. That's just calculator talk. So 4.09 times 10 to the negative 19th joules. Final answer. Just in case you did it with the system of equations, let me show you what that setup looks like. It's kind of a lot to do in one step, I think, for most people. But here it is if you want to pause that and check that out. Let's have you try this last one all by yourself. It's not two separate steps. You do have the issue of nanometer to meter before you can start plugging into the frequency equals speed of light. Nu equals speed of light over lambda equation. Well, frequency equals speed of light over wavelength, same thing. But it's not asking for the energy. So this is like half the steps that we just went through, but you do have to deal with those nanometers. So give this a shot. And we should get 5.379 times 10 to the 14th hertz. Or you could leave it as 1/seconds, but since the SI unit is hertz, I would switch it back to that. If you did the nanometer conversion separately like I did, I almost always do it that way, it's 5.57 times 10 to the negative 7th meters. Just kind of do that first and then plug it in like that. There's one last thing that can go wrong in the calculator. If you haven't noticed by now, I have huge calculator trust issues, so I'm trying to help you avoid my pitfalls. Alright guys, that concludes our second set of notes in Unit 2. The next set of notes that you're looking for is Unit 2 Notes C. It's all about electron arrangement. We're going to really dig into quantum mechanics, so be ready.